Well, hey everybody, welcome back to Master the NEC, sponsored by Electrical Code Academy Incorporated. We're in part 2. Now, if you haven't watched part 1, we're talking about grounding electrode systems. And kind of a recap, in part 1, we went over the fact that 250.50 requires that all grounding electrodes that are present have to be all tied together and they act as one system. We also went on to describe what a underground water pipe ground, which is 250.52A1, and the metal underground water pipe, we described it 10 feet in length, continuous. Any broken segment has to have a bonding jumper to maintain the continuous 10 foot or more in contact with the earth. We even talked about what happens if it's wrapped in some type of wrap and it's not really present because it's not really in contact with the earth. If it's not there, then it's not present, then it's not an electrode you can use. We also talked about supplementing it and what's required if it is a water pipe ground, that you are required to supplement it. So, in the description below, there should be a link to episode 1, or at the end of this video, I will make sure that it will link to episode 1, or somehow you need to go find episode 1, and it always is going to be available over on our YouTube channel, youtube.com/masterthenec. Okay, so in this episode here, we're going to move forward a little bit, and we already assume you watched episode 1. You understand that we have the grounding electrode system. Now we're going to move on to 250.52A2. And this one is the metal in-ground support structure steel. So we're going to move on to that one. So if you got your code books, we're going to be in 250.52, and we're going to be looking at A2. And we're also going to knock out A3 in this episode as well, which is a concrete encased electrode. So let's go on and get over to our lesson. And so here's where we're at, 250.52A2. It's metal in-ground support structure. So here's the requirement. Now, this can be the same as it is in the code, but we have it and we want to make sure. Now, it's highlighted here because it's a direct extraction from the NEC. And I should also mention that we are working out of our Fast Tracks Purple program. That is our grounding and bonding program. It's available in the 2017 or the 2020 edition. This is the 2020 edition. And it's a great course to really go deep in grounding and bonding. So if you're interested in it, check it out over on our website, electricalcodeacademy.com, .net.org. It doesn't matter. masterthenec.com. It really doesn't matter. All those roads lead to our programs. But what you're looking for is the Fast Tracks Purple program. That is our grounding and bonding program. Okay. All right, so let's talk about this metal in-ground support structure. What are we talking about here? So the requirement, it says one or more metal in-ground support structures in direct contact with the earth vertically for 10 feet or more, with or without concrete encasement. So that means they can be driven down or dug out and put in the ground and then concrete around them, either or. It says if multiple metal in-ground support structures are present at a building or structure, it shall be permissible to bond only one into the grounding electrode system. So if you have these in-ground steel supports all over the place supporting the building, you don't have to go connecting them all together. We just need one that's going to give us 10 feet or more in contact with the earth, or in concrete in contact with the earth. And that's all we need for this electrode. Okay. All right. So again, there's also an informational note here. It says metal in-ground support structures include, but are not limited to, pilings, castings, or other structural metal. Most of the time, what we see these as an I-beam driven into the earth, and it's making that contact. Think of it as a big ground rod, but it is in-ground structural steel. Okay. Now, the discussion, as you see on the screen, it says, it is clear in the definition that to be a grounding electrode, it must be in contact with the earth. Any portion of the metal piling or casing that is above ground may function as a bonding conductor to bond grounding electrodes together. So you're using it as a bonding component, kind of like we did for the 5 feet of the water pipe ground when it came in the house for bonding purposes. Or you can use it as a grounding electrode conductor. Now, we'd have to look at 250.68C2. But if you have the structural metal steel of the building, then you can use that to interconnect the electrodes, okay, things like that. So again, not for right now. We're going to get into that as we go into other episodes with grounding and bonding. We got a lot of things coming up in 2022, and I told you the videos would start rolling out, so they're going to be coming out. So we're most certainly going to be talking about all these other aspects of bonding different electrodes together and whatnot in a program. All right, now it says, as explained in the informational note, metal in-ground support structures typically consist of pilings, casings, or other similar structures. These are often driven into the ground by a pile driver, actually driving it down piece by piece, a ramrod, okay? And it does provide adequate support for the entire structure. In fact, structures are built off of this type of design, okay? Now, when these pilings or casings consist of 10 feet or more of metal that is conductive and in contact with the earth, they create an effective grounding electrode. Remember, it's not just about being driven, okay? They can also be in the ground encased in concrete, okay? So keep that in mind. You have different options. Now, let's see what it looks like, because if you've never run into these, and as an electrician, by the time you get to the game, the chances are you'd have to look at the drawings. The engineer would design this out. This is obviously something that would be an engineering design, so you don't have to worry about that. But let's go on and look a little bit. So here's what we're talking about. Let's kind of give a look-see here. So here you can see two options here. You see the one on the left, which happens to be one that's encased in concrete, but it doesn't have to be. It can be driven, like the one on the right, okay? Now notice that portion above grade, that is bolted to the portion that's below grade. That under 250.68C2, that is being utilized as a grounding electrode conductor. And you can also use it to tie other electrodes together, okay? So that's kind of what we're looking at here, but you'd have to go read 250.68C2 to get the full breadth of that. So feel free to pause the video and go check that out if you want. We're kind of focusing on the electrode itself, which is the in-ground steel that we see here. So that's your electrode. And that is, again, part of, remember what we said in the video, part one? These are kind of inherent to construction, right? They're part of the construction. They're supporting the building. From an electrician's standpoint, I only have to make a connection to it that goes all the way back to my panel, my service panel, right? I need to make that connection. Now, interesting enough, when people say, well, what's the size of the grounding electrode conductor? Let's say this right here that's making that connection. Well, that's going to be based on the size of the service entrance conductors, right? Okay, so it's not a rod, pipe, or plate. It's not a UFR, okay? Not a ground ring. So I don't have the luxury of going to 250.66 and go to A, B, or C. So what that means is I'm going to use the table, okay, in 250.66 in order to do my sizing, okay? And if you look at that table, you'll notice pretty quickly that that table is based on ungrounded conductors or the equivalent area of parallel ungrounded conductors, okay? So it's dealing with the service aspect of it, all right, for this case. Now, we can't totally say service because if this was a detached structure, another one being fed from another building, then you're still required to establish the grounding electrode system at that building as well. And you could have in-ground steel there as well, right? The only difference is over there, you're going to make the connection from, let's say, a separate building that's being fed by a feeder. If you have the grounding electrode system there for that building, then you're going to be making the grounding electrode conductor connection up to the equipment grounding terminal bus, not to the neutral. Again, remember, separation. Okay. So, and I'll remind people, if you didn't get a chance to catch the coffee hour on the main bonding jumper, we do touch a little bit on the separation and remote distribution panels, or as some people call them, sub panels. We did touch on that a little bit. So go over to the YouTube channel and look for it in my channel, and you will find that video saying main bonding jumper and sizing. It's a really good video, so I encourage you to go check that out. And subscribe to the channel, because you don't know what we're coming out with, and we have a lot of stuff coming here in 2022, I promise you. All right, so now let's move on to the second point of today's topic, concrete encased electrodes. Now, concrete encased electrodes, again referred to as UFR grounds because of Herb UFR and all the work that he did way back in the 60s. Reality is it took more than Herb UFR to do that. Now, if you have our grounding and bonding course, there is an addendum to that actually tells you the history of how the concrete encased electrode came to be. So it was more than just what Mr. Ufer did in his testing. It took the collaboration between electrical inspectors all around the country, mainly on the West Coast, who together put their heads together and really worked out the rules for a concrete encased electrode, okay, which we affectionately call today a Ufer ground, but it is a concrete encased electrode. Okay, so if you look at 250.52A3, this one, now this is again one of the first three. Remember we said that in part 1 of this video series? That means that it's usually inherent in the construction. So it's in the footing, right? Which is something the electrician's really not going to do. We got to make a connection to it, but it's not something we typically are responsible for. Okay, now, of course, they could stub the rebar up where our panel is, and we make that connection there. It's got to have access to it. Can't be outdoors, got to be indoors. Okay, we can make that connection, or it's usually in the wall with an access. Or we could take the 4 copper, it doesn't have to be larger than a 4. Okay, if you go read that in 250.66, and you get, believe it's B, and you look at that, then it doesn't have to be larger than a 4. But again, that could go all the way down and make the connection to the rebar down in the footer, or it could run 20 feet of it down encased in 2 inches of concrete down in the footer. That's an option as well, okay? But these three, A1, A2, and A3, are inherent with construction. It's not something that the electrician has to add, okay? Now, you could add the concrete encased electrode if you get there in time, okay, to do this, right? Hopefully you're coordinated with somebody stubs up a piece of rebar or something. Now, most people today aren't running the copper because people are just cutting it off at the foundation, right at the top of the slab. And that's not a good thing, okay? So let's read what we've got here. What are the requirements for this concrete encased electrode? A concrete encased grounding electrode is required to consist of at least 20 feet of either 1 or 2. So we got 2 options, but 20 feet is still there, either one. Number 1, it says 1 or more bare or zinc galvanized or other electrically conductive coated steel reinforcing bar or rod of not less than a ½ inch in diameter, installed in one continuous 20-foot length, or if in multiple pieces, connected together by usual steel tie wires, exothermically welded, welding, or other effective means to create 20 feet or greater length. Okay, so inside of the footer, you typically will have your rebar, and it'll be pieces, but it's all tied together. So collectively, you're going to have at least 20 feet in contact with the earth in this rebar that's encased in 2 inches of concrete. And so you've got this concrete encased electrode. Now, I said this in a previous video, part 1, that if somebody put down a vapor barrier underneath that footing, that footer, and so the concrete with the rebar wasn't in contact with the earth, then guess what? You do not have a concrete encased electrode. It's not in contact with the earth because it's required to be in direct contact. So that's important. So if you're somewhere in the country where they have the viscreen down to this vapor barrier, and they might allow you to cut that to expose 20 feet of the rebar and concrete in contact with the earth. But again, in some areas where they require that vapor barrier, that kind of defeats the purpose. So you got to be very careful and understand what's going on and where it's being installed to determine whether or not. It's kind of like that water pipe ground, right? If they wrap it in something and the metal's not in contact with the earth, then it's not a water pipe ground electrode. So same thing with the UFER. If it's not, if the concrete that encapsulates the rebar is not in contact with the earth, then guess what? It's not a concrete encased electrode, right? So that's what you do with the rebar. Now, the option number 2 is I could use bare copper conductor, not smaller than a 4 gauge. And it still needs to be 20 feet, right? It's still going to be installed in the footer. And again, that concrete with that 20 feet of bare, okay, has to be in contact with the earth, okay? Now, the whole premise behind this was to string out that 20 feet. There's been a lot of people that argue and debate, could I just take a coil and throw it in? I am under the belief that it has to be strung out for 20 feet. Some people say that, well, 20 feet of copper 4-gauge is 20 feet. I believe that it needs to be stretched out. It needs to be 20 feet. You can agree to disagree. We can have that debate. But I believe that is the proper way that it was intended so that it can have full contact with the earth. Okay, that type of thing. All right, so anyway, well, full contact in the concrete in contact with the earth. All right, now it says metallic components are required to be encased in at least 2 inches. That's either the rebar or that bare copper has to be encased in at least 2 inches of concrete and be located horizontally. That's the other thing that makes me think you have to lay this out. Horizontally within that portion of the concrete foundation or footer that is in direct contact with the earth, or within vertical foundations or structural components or members that are in direct contact with the earth. So you're allowed to do it horizontally, but in some cases you can do it vertically. If, again, you have the earth is up against it and you have a vertical wall and that is part of the footing or foundation, then it would be okay, horizontally or vertically. Okay, we wouldn't have any problem either way with that. The key thing is that concrete that encases it has to be in contact with the earth. Okay, now if you use one vertically, now in this case, if it's vertical and they backfill and there's some type of membrane that gets put over the side of the wall or the footer or the pour, then it's not really in contact with the earth. So many things that you got to think about, right? The other thing to remind you, if there are multiple concrete electrodes present in this building or structure, you only have to do one that meets the intent, which is 20 feet. Okay, so you don't have to connect them all together if you have multiples. Okay, only got to do one in order to achieve this. So what does this look like? Well, let's kind of give it a look if you haven't not familiar with one of these. So here we go. We'll kind of give it a look-see here. So what we've got here is you can see where it could be the vertical, and let me make sure I get my mouse on the screen with you. It could be vertical this way, okay? Or it could be horizontal this way, okay? So key, encased in at least 2 inches of concrete, okay? So it's got to have 2 inches around it, all right? And then it is in the foundation or footer that is in direct contact with the earth, okay? And it can be vertical or horizontal, not a problem. It definitely needs to be 20 feet, whether it's a 4-gauge copper or if it's the 1/2 inch diameter rebar, okay? It has to be in this concrete, encased in it, in contact with the earth. If for some reason, again, there's a vapor barrier here, then it is not. Or there's some type of vapor barrier on the side, okay? It is not. Now, this is a good example of pieces tied together. So I can get 20 feet of pieces tied together. I just need 20 feet if I'm going to use the rebar 1/2 inch, 20 feet. And it can be both horizontally or in the vertical concrete. The key here is contact with the earth, okay? And you'll see here in our program, not only do we have the addendum, but it also gets into a discussion that talks about the history where they did the testing. And again, back in the 40s and in the 50s, and then, of course, the research paper that Herb Ufer all was based on in the 60s. And here you see the Appendix B. So in this course, we have an appendix, and you get that to go over to the book that's included. Then you go to the appendix, and it is an amazing read. Okay, it was all the testing and the investigation that was done. If you've ever wanted to know the history of how it came to be and everybody that was involved in all of this, it is definitely worth the read, okay? Pound for pound, okay, a Ufer ground is probably the best grounding electrode out there. Pound for pound, it's inherent in the construction in many cases. Usually it's in most buildings, whether it's commercial or residential, but again, whether or not it's in contact with the earth because of vapor barriers and all those type of things, that's going to be something that you have to determine. Now, the good thing is everybody knows that the rebar has to work in conjunction with the concrete, right? So the hyperscopic nature means the absorption of moisture of concrete really lowers that contact resistance down. So you think of the two working together. The rebar or the 4-gauge copper, whatever you choose, working in conjunction with the concrete allows to have a really low resistance. And that makes it a really, really good electrode. The other thing about it, it is really good electrode where you get very little rain, because the rain that you get, when you get it, hydroscopically is absorbed into the concrete and, again, allows for really low contact resistance. So it is probably, pound for pound, the best out there. So keep that in mind. But also remember all the little things I said about it, okay? It's important that if it's have a vapor barrier, then guess what? You don't have one. Make sense? Okay. And remember, if I had, I wouldn't have to do all, I only have to do one. So if I have multiple, let me give you an example. So I could have concrete, let me make sure I come back to me so I can give you this example here. Let me give you another example. So I could have a situation where I have concrete encased electrode, but we have basically piers, and it's of concrete and rebar, and it's a bunch of them. Well, as long as I've got vertically or horizontally, but in this case, say vertical piers, as long as I've got 20 feet of rebar connected together, could be sections connected together, but if I have it and it's in contact with the earth, then I would only need to bond to one of those piers, okay? That's basically the rebar form that's in the ground, and then you put the concrete around it, that type of thing. That would qualify. But what it's telling me is I don't have to do all of them. So if I've got another one over there, because I have different piers, okay? And we're not talking about in-ground steel, okay, where the steel is. We're talking about concrete with rebar, and then you have the J-bolts, and you have all that, and you have a hot top plate, and you mount onto that support a structure. If you dig the hole, sterno tube, put in the rebar, that type of thing, and now you've got the concrete in contact with the earth. Now be careful, because usually on those, the tube is only the first part to help keep it round. You better make sure that you have the concrete in contact with the rebar, in contact with the earth to qualify as a concrete encased electrode. Now, assuming it does, whether it's vertically or horizontally, you have the 20 feet that's required of 1/2 inch diameter rebar. Assuming you have that, then you don't need to use the other ones that might be there in the structure. You only need one. So you don't need to tie them all together. A lot of people think you do. You don't. You just need to meet the one. That's it. The other thing I'll remind you before we end this episode is there is no need for a supplemental to a concrete encased electrode. Unlike ground rods, plates, and pipes, or water pipe grounds, you do not have to supplement a concrete encased electrode. If you've got one, then you're golden, right? And remember, and we're not going to touch on this, but the size of the grounding electrode conductor from the grounded terminal bus inside of the actual panel service equipment down to the electrode does not have to be larger than a 4-gauge copper, right? And you need to go look that up if you're confused about that in 250.66B, I believe. So let me go look it up. I won't take you away from the screen. I want to make sure it's B. Because, again, I do a lot of teaching, so I want to make sure I get it right. And I'm pretty sure I'm right. But let's look and see. Absolutely, it is B, 250.66B. That allows you, it tells you that it does not have to be larger than a 4 AWG copper. Now, can it be larger? Absolutely. Can an engineer specify it larger if they want? But it doesn't have to be larger, okay? So you gotta go read the history and how they developed the concrete encased electrode and what sizes they use to establish everything, and you'll get an understanding why it doesn't have to be larger than a 4. So hopefully you got something out of this episode. This was part 2. We're gonna move on to ground rings in the next one and give you additional insight on those as well. But hopefully you got something out of this series. We're keeping them short, keeping them sweet, and keeping them educational. Until next time, folks, stay safe. God bless.